This is Babak. You know me already. I introduced myself. I work with Dr. Hashemi, and my area of research is mostly in computing networks, edge computing, 5G, and the tools that I'm using in my research are mostly reinforcement learning methods, Bandit algorithms, and this sort of stuff. Today, I'm going to talk about our work, which is titled Energy Efficient Deadline Ladder Task Offloading, a multi-user, multi-channel bandit approach. And I'll go over this work by first introducing the concept of computing network. What is a computing network? What a computing network consists of? And then I'll go over our problem, the motivation behind it, and give you guys use case of our research. And then provide you guys with two different solutions that we provided and we developed over time. Okay, so a computing network consists of three different elements. As you can see here in this picture, we have cloud servers on the internet. We have which are responsible for performing our computation and storing our data. We have edge network or cellular network, which is responsible for transporting that data from the cloud servers to us. And then at the end of the day, we have edge devices, our cell phone, our watches, our smart devices at home. And all of these are considered edge devices or IoT devices as well. These are three main components of a computing network. But what is happening? So if you look at this picture again, actually, most of the data was generated and stored at the clouds and then transferred through the network to the edge device. But nowadays, the data generation is shifting toward the edge of the network. Why and how this is happening? This is happening because of the appearance of AI, the Internet of Things. An autonomous vehicle can produce up to 4 terabytes of data per day. A smart factory can produce 5 terabytes of video stream per day. All of these data is generated at the edge of the network. Some of them need to be processed. You need, for an autonomous vehicle, you need to make a lot of decisions. And sending back the whole data through the internet to the cloud servers and getting back the result of your computation consumes a lot of resources. And we want to avoid that resource consumption. We want to reduce the cost of the whole process. But how is this possible? How this whole data generation, we can produce this amount of data? One of the enabling technology for this huge amount of data generation is 5G. 5G cellular networks can provide up to 10 gigabytes of data per second for us. And it can provide a very low latency for us. And all of these means that every day more and more data will reach the cell towers, 5G cell towers. But what is the problem? Okay, the data is generated, reaches the cell towers, you will communicate it and transport it to the cloud servers, compute our task, do whatever we want to do with our data, and then send it back to the edge devices. What's the problem here? The problem is that we look at the problem from three different aspects. The first aspect is the internet aspect. Sending back the whole data consumes a lot of bandwidth. We need a lot of backhaul bandwidth at the back of the cell towers to send back the data. 4 terabytes for one vehicle is a huge amount of data. And a lot of these applications that we are seeing, AI applications, they need a very low latency. And sending back the whole data through internet introduces a high latency for those applications. What we can do instead, is that we can bring a computational server, a huge server, and put it next to a cell tower. Put it next to near the edge of the network, where our cell phone is located, where the autonomous car are located. And this leads to low latency computation. We can compute our task very fast. This also saves us some network bandwidth. We can use that bandwidth for some other orders. And it also reduces the expense. All of this happens by just processing the data at the edge and discarding it. Because most of this data will never be stored in any place. They will just be processed and we get some result out of them, and that's it. Another aspect that we are looking at the problem, if you imagine the first picture I showed you, there were 3 elements: cloud servers, edge devices, and the cellular network. So the second aspect that we are looking at is edge devices. Edge devices for us are UAVs, drones, cell phones, autonomous cars, virtual reality glasses. All of these smartwatches are edge devices. All of these devices have limited computational resources. Your watch, my watch, has a very not very powerful CPU, and it has a limited energy storage. The battery lasts maybe 1 day. And there are many tasks for example, for autonomous cars that are very safe, latency sensitive. But what we can do to overcome this challenge? Again, if we have computing power, a computing resource server at the edge of the network, we can just communicate with that server and send out our task to that server and get our results back. But is that all? So we consider 2 different aspects, and both of those aspects resulted in the same answer. Just add a computing server at the edge of the network. But that's not all. If you look at the edge network, or 5G in particular, 5G enables edge devices to access the network through different bands. And each of these bands, the spectrum bands, have different characteristics. Lower bands usually provide a wider coverage, but they have smaller bandwidths. You can also use them with consuming lower amount of power. They have a lower power consumption. Higher bands, on the other hand, they have a smaller coverage area, but we can have a huge bandwidth. We can transfer a huge amount of data at a tiny fraction of time, but we also need more power. So these are some trade-offs that we need to consider. Which band is better? If we look at the whole picture, adding a server solves some problems, solve the limited computational power, solve the low latency computation requirement, but should we really use that server all the time? Is it an energy efficient solution to offload all of the tasks? We use the server all the time. If not, when and where, under which circumstances we need to offload and use that server. These are the type of the questions we want to answer. Is there any trade-off between the energy efficiency, communication channel quality, the latency that we require for a task? Is there any trade-off between them? We're going to answer these sort of questions. Let me give you a use case of our research to make it more clear for you guys. Consider that we have an autonomous UAV flying around. UAVs usually have limited computational power, a small CPU. And their battery usually lasts for 3 hours, most like 5 hours, not that much. And consider this UAV is operating in a search and rescue mission. We want this UAV to be able to operate as long as possible, like the longest amount of time possible that we can operate in that rescue mission. And we wanted to find people who may need some help and notify the command center. All of these are really heavy computational tasks. The UAV can do it by itself, but the problem is it requires it provides a higher latency for the task to be completed, and also it leads to depleting its battery sooner. And most of these UAVs are equipped with multiple communication technologies such as Wi-Fi, cellular network, LTE, 5G, LoRa, and many other technologies. So here, again, the question is, which technology is better? Which band is better? Should we always use the server over there, or no? So all of these questions, all of these are formulated into this picture that we are seeing here, these two pictures that we are seeing here. And we have a network of edge devices operating alongside each other in a heterogeneous network. We have heavy computational load. We have limited computational resources and energy storages. And most of the tasks that we are doing are delay sensitive. And these UAVs or these edge devices usually can communicate with the network, edge network, through different technologies and different spectrum bands. Additional computing power is also, we said, is enabled. We added to the network, and now we want to decide which communication channel is better. Should we always do offload to the edge server or not? The initial work that we done was published on 2021 ACM Symposium on Edge Computing. And in this work, which was in collaboration with Dr. King, Dr. Hashemi, and our colleagues in USRA, in this work we considered edge devices and we considered UAVs in specific. And we equated all of these UAVs with the DQN, and we considered 4 different communication channels with 4 different frequencies, operating at 4 different frequency range, from 600 megahertz to 5.9 gigahertz. And our goal in this paper was to maximize the system lifetime. We have a fleet of UAVs and we want to maximize the lifetime over the whole fleet. And how we define the lifetime, the moment that the first UAV depletes its battery is the definition of the system lifetime for us. So we consider the whole system as a whole and then try to maximize the lifetime. We did this work and then realized that there are some aspects of the problem that we never considered in this work. example, we didn't consider the latency of the task. And we also realized that the tasks can be modeled independent of each other. The amount of energy I consume to compute one task doesn't depend on the other task. So we developed our model, we worked on our model and equipped it with a more powerful learning algorithm that also provides us some theoretical guarantee as well, and came up with this configuration here, this system model here, where we have tasks that are to the edge devices. These tasks are modeled by size, computational intensity, and deadline. And then our decision, our agent, choose to whether locally compute the task using the local processing or upload it to the edge server to be calculated there, to be computed there using one of the communication channels or communication technologies available to it. These tasks along the way wait in different queues. They have waiting times. They consume some energy. So the question is, where is the trade-off between that energy consumption and the latency provided? Should we, again, offload the task to a nearby base station? We answered this question in this paper, and our goal was to get the highest energy efficiency while providing the minimum task response time, while meeting the deadline. And the definition of you may ask, what is the definition of energy efficiency? By energy efficiency, we mean the lowest amount of energy consumption per unit of task size, the lowest amount of energy we consume to calculate a specific task. This work showed some good, promising results. Initial investigations that we had showed very promising results against optimal strategies. And we compared it in 3 different ways: fractional tasks that have met their deadlines, the energy consumption, the response time, and all of those, we considered them and compared them with optimal strategies, and they're all showing good results. And with that, I conclude my presentation. So, a couple of points that I want to conclude is that we realize that more and more data will be generated at the edge of the network, and that will introduce some challenges for us, for the network, for the edge devices, for the edge network, cellular networks, and all of them. And we try to add a computing server at the edge of the network and solve all of those problems, but there are still other challenges that need to be tackled. And we investigated those challenges and tried to tackle the trade-off between the latency and energy consumption in the edge devices, and we provided a learning algorithm for that purpose. With that, yes, and most of the statistics that I've got and presented in this presentation are taken from this report here. And with that, I'll answer any questions.